Hello and welcome. These are the solutions to quiz 29. So how much energy does electromagnetic radiation of wavelength 225 nanometers contain in kJs per mole? Okay, so this wavelength range here would be in the ultraviolet range. It's a relatively high energy range, higher energy than the visible region. And so the way we'd go about calculating the energy of these photons in kJs per mole is to use the equation to calculate the energy per photon. So the energy of a single photon is calculated with the equations either h nu or hc divided by lambda. And so what I would do here is I would use hc divided by lambda, so 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. So the per second cancels with the seconds and Planck's constant. And divide by the wavelength, but we want to go into meters. 225 nanometers, 1 nanometer is 10 to the minus 9 meters. And if we're not writing our units out, we may have never converted this. So we want to write our units out. So we see here, we want to put the lambda into units of meters. So this gives us the energy of a single photon. So we go 6.626 times 10 to the minus 34 times 2.998, 10 to the 8, divide by 225 e minus 9, or times 10 to the minus 9, gives me 8.83 times 10 to the minus 19. Joules, but that's per photon. If I want to go to kJs per mole, I just have to account for having an Avogadro's number of photons. So there's 6.022 times 10 to the 23 photons in a mole. And of course, there's 1,000 joules in a kJ. So if I want to go to the kJs per mole of this radiation, I just use Avogadro's number and convert to kJs. So that gives me 532. It's pretty high energy photon of light. This would be capable of breaking perhaps a bond in a molecule that had a bond strength of 532 kJs per mole or less. It couldn't break a stronger bond than this because it doesn't carry enough energy per photon to break that type of bond. Okay, next question down is asking for the minimum possible uncertainty in the measurement of the position of an electron in angstrom with a measured velocity of 4.00 plus or minus 0.10 times 10 to the 6 meters per second. We're given a couple of equations. One of them is given to actually trip us up. This is the Berkeley wavelength equation for the wavelength of matter as a function of Planck's constant, the mass of the particle, and v here is the velocity of the particle. The equation we need for this problem is the uncertainty principle that says the uncertainty in the position times the mass of the particle times the uncertainty in the velocity of the particle must be greater than or equal to h divided by 4 pi. And we're given the mass of because this is dealing with an electron, we're given the mass of the electron in kilograms. So we're going to use this equation here. There's a little apprehension of, I wish like our equation sheet would give exams directly on it. I think, if we need to solve a math problem with the uncertainty principle, that we would give the equation kind of like we do here within the problem. And so we're going to solve for the uncertainty. The minimum possible uncertainty in the position of the electron must be greater than or equal to h divided by 4 pi m delta v. But the delta v here is the uncertainty in the velocity. It's not the change in the velocity. It's really the uncertainty in the velocity is what the delta v means. And it's the 0.10. So this is equal to 0.10 times 10 to the 6 meters per second. So it's 0.10 times 10 to the 6 meters per second. So when we plug in here, let me plug it in. Let's plug it in here, I guess. So delta x must be greater than or equal to 6.626 times 10 to the minus 34 joules times seconds. Now a joule is a kilogram meter squared per second squared. Joule times seconds is the units of h. Then we're going to divide this by 4 pi times the mass of the particle, and then times the uncertainty and the velocity. Now what's canceling? The seconds are canceling. One of the meters cancels and the kilogram cancels. And the mass has to be in kilograms due to the units of joules and its fundamental relationship to kilograms. 1 joule, 1 kilogram, meters squared per second squared. We're also putting things in SI units. If you recall, the SI unit of mass is kilograms. So we take 6.626 times 10 to the minus 34, divide by parentheses 4 times pi times 9.109 e minus 31 times 0.1 e6. That gives me 5.8 times 10 to the minus 10, which is 5.8 angstrom. So 10 to the minus 10 meters is 1 angstrom. 1 angstrom is really small. So this is 5.8 angstroms. So there we go. Now the next problem down is going to be the de Broglie wavelength problem, h divided by mv, for the wavelength of a particle as a function of its mass and velocity. Now the issue here is the lower the mass, then the greater the wavelength. So the more wavelength behavior you have is for when particle masses are really low. Okay, so our wavelength is equal to h divided by mv, so 6.626 times 10 to the minus 34 joules times seconds. So again, it'll be kilogram meters squared per second squared times seconds. That helps me make sure I use my units in the right, puts my values in the right units. Sometimes on exams, they'll give you a mass in grams, and the simple mistake that everyone makes is not converting to kilograms. But really the mistake a lot of people make is just not writing their units out when they solve problems as a matter of habit. But if you make writing units as a matter of habit, we're relatively rarely going to make a mistake in a math problem like this one here. Now the velocity we plug in here is just the actual velocity itself. It's the 3.00. The numbers actually changed for this problem, times 10 to the 5. So the velocity and uncertainty is different than the previous example. So 3.00 times 10 to the 5 is our velocity. And the uncertainty means nothing here. We don't need to use that value for this problem. It's just meant to be there so that when we're doing the uncertainty principle, we use the uncertainty. And we're doing the problem here, we're using the velocity itself. So 6.626 times 10 to the minus 34, divide by 9.109 times 10 to the minus 31, divide by 3.00 E5, gives me a value that rounds to about 2 times 10 to the minus 10, it looks like. You can switch to scientific notation, like my calculator right now, just a TI-30 says like 0.000000 something 2. But you can go and actually change to scientific notation mode. And there it shows me it's 2.4 times 10 to the minus 9. Actually have 3 sig figs here. 2.42 times 10 to the minus 9. And that's meters. How do I know this is meters? Well, their seconds cancel. Meter, one of them cancels. We're left with one of the meters left behind. We want this uncertain, or the wavelength in nanometers. 1 meter, 10 to the plus 9 nanometers. So I'm multiplying by 1 E9. Need to switch back to normal mode. 2.42 nanometers. Okay. So what does the Heisenberg uncertainty principle claim? Matter and energy are the same thing. That's not what it's claiming. It's impossible to know anything with certainty. That's not what it's implying. I once heard that in an English class when I was an undergrad. Somebody used as an argument for something they were trying to make in some English class. I'm like, okay, I don't think that's exactly what Heisenberg meant. It's uncertainty, or it's impossible to simultaneously measure the exact position and momentum of an electron. And this is true of actually any particle, but it's most important or relative to the electron because it has a really low mass. And as soon as you start making the mass bigger, then if you start to think of the uncertainty principle equation up here, if you make this mass bigger, then you're going to start to have a situation where you can have a pretty good, precise understanding of both the velocity and the position. Like we did this with a baseball. We said, okay, if your uncertainty is plus or minus 2 miles per hour, what's your certainty in the position? It was like 10 to the minus 31 meters. Like, it's not infinite precision, but there is still some fundamental limit, but it's pretty much like you can know exactly, practically speaking, where the baseball was the moment you know its velocity with some relative uncertainty. So this is the biggest problem with electrons. Measurements taken in the laboratory are subject to some amount of error. That really has nothing to do with the uncertainty principle. I've heard, like, sometimes you do see a misuse of the uncertainty principle where you sometimes hear the notion that the very act of trying to measure the velocity changes the velocity. That's really not what the uncertainty principle is about. It's just an inherent inability to know the two quantities at the same time. It doesn't have to do with when you try to measure it, you're fundamentally changing what you're trying to observe. It's not entirely. You just have a limit on what it is you're capable of observing. So, like, if you're thinking the thing you're trying to observe changes as you try to observe it, you may think, well, if you get a better detector, then you can precisely know both the position and the velocity, and that turns out not to be true. It is unclear whether atoms possess electrons or if electrons possess atoms. Like, I'm laughing. I can't remember how long ago it was I wrote that wrong choice and how silly it is, but that's pretty clearly not the right answer. Okay. Moving on to the next page. Wavelength of light. Which wavelength of light below has the greatest frequency? Okay, so C is equal to lambda times nu. And so the greatest frequency is going to come from the measurement that or the photon that has the lowest and smallest wavelength. And so the smallest wavelength, I'm just inspecting the units here. I got 2 in nanometers. And so this is a really high wavelength. This is going to have a really low frequency. So it's not going to be the meters. Same with the micrometers and the millimeters. So it's going to be the nanometers that is of the smallest possible wavelength. So 254 nanometers is smaller. Now we could go solve for all the frequencies for these values and compare. The key is that all of these wavelengths of light have the same speed of light. They all travel at the same speed of light. So if you want the photon with the greatest frequency, you need to have the smallest lambda. Which of the following statements is true about electromagnetic radiation? So gamma rays are greater in energy per photon than visible light. That's true. Gamma rays are the highest. Kind of, you go like the gamma rays, X-rays. Actually, the greater sign would be the other way around. So gamma rays have the greatest energy, followed by X-rays, followed by UV rays, followed by visible rays, IR, microwave, and then the smallest energy per photon would be the radio frequency. Blue light has a greater frequency than red light. Let's think about this for a minute. So blue is on the 400 nanometer side, red is on the 750 nanometer side, and you get this backwards Roy G. Biv color. So blue is closer to the 400 nanometer, red is on the very top of the visible region at 750 nanometers. And so blue light, if you think of blue light, has a lower wavelength, so it has to have a greater frequency. So yes, blue light should have a greater frequency than red light. Blue light has a greater energy than red light as well. Greater energy, greater frequency. Per photon, red light has a greater energy than blue light. No, we were just saying previously that it's the other way around. Higher energy goes with higher frequency. This is the high energy side. This is going towards the UV. This is going towards the IR. So red's on the lower energy side, blue's on the higher energy side of visible light. The wavelength of infrared radiation is less than ultraviolet radiation. No, the wavelength of the infrared radiation is greater. So wavelength is beyond 750 nanometers. So the wavelength of infrared radiation is greater than ultraviolet. So 1 and 2 look to be true here. It's always sometimes useful to make sure, like when we get these questions, we're looking for the true statement. Sometimes it says which statements are false and it gets a little screwy, but we're looking for the true statements. The true statements are the first two. The reason why I mention that is if this says like which statements are false, usually we're like check marking the true statement still, and so it gets a little bit wonky if we forget what it was that we're looking for, but we had a good hold on that one. So what is the delta H for the reaction, the value for delta H for the below reaction is minus 1107 kJs. So delta H, this reaction minus 1107 kJs. How much heat is released or absorbed when 5.75 grams of barium oxide is produced. So we're producing product, so the reaction is going forward to make product. The delta H is negative, implying the reaction is exothermic. The reaction gives off heat. So heat should be released by this reaction, not absorbed. In the Q reaction always just plugs the sign in for delta H. So to solve for Q reaction, I don't need to worry too much about the math. Or I don't need to really think too much about the sign. I'm just plugging in the sign as is for delta H. So my barium oxide, I need the molar mass of barium. Find a periodic table. So barium's 137.3 plus 16. It's 153.6. And then the key is this 2. For every 2 moles of barium oxide that are produced, the Q reaction is minus 1207 kJs. So I'm just plugging in the sign. I'm not even thinking about the sign. I kind of already thought about the sign that heat should be released. I'm going back to calculate Q reaction and just plugging in the sign and kind of doing the math. Forgetting about interpreting the sign, we'll interpret it after the problem. Oh, it's not 12, it's 1107. Where did I write 1207 first? Just here. So it's minus 1107, not 1207. Wrote the number in wrong. Divide by 2. So it's negative 20.7. Did I round wrong? It's probably 20.8. No, this is 153.3. I said 153.6. 153.3. So if we want to get it dead on, this should get it. It was off by a tenth, but it shouldn't be off by a tenth. There we go, minus 20.8. 153.3 grams per mole for barium oxide, and 2 moles, minus 1107 kJs. 20.8 kJs is the Q reaction. So the reaction is losing heat, and that heat is going to the surroundings. So it's releasing 20.8 kJs. So 20.8 kilojoules is released. Number 8, when an acid and base originally at 25 degrees are mixed in a beaker, the temperature of the solution rises to 35 degrees C. The key here is the word solution. Which statement is true? The reaction is endothermic because it absorbs heat from its surroundings. A lot of people go with this answer. This is wrong. The reaction isn't absorbing. If the reaction absorbed heat, the solution temperature would drop because it would have taken the solution's heat in order for the reaction to take place. And so an endothermic reaction should make the temperature of the solution drop. So the reaction is exothermic because it releases heat. The temperature is going up because that reaction released heat to the surroundings. And I say this a lot, you can't really put a thermometer on the reaction. You can put a thermometer on the surroundings of the reaction. So the temperature of the surroundings here is what increases, and the Q of the surroundings therefore increases. But the Q reaction, always negative Q of the surroundings. So if the heat of the surroundings goes up, heat of the reaction goes down, and is hence exothermic. So again, the reaction is releasing heat. That's why the solution temperature is going up. All right, that's all for this video.